So the lecture on Monday, yesterday, already covered problem 20. So it's a decay rate problem. It's a decay rate. So you have radioactive material that's decaying. So the only difference between a growth problem and a decay problem, an exponential growth and exponential decay, is that the R value is negative. The rate is negative because it's decreasing instead of increasing. So this number 20 was covered last lecture. So my advice would be, if I were prepping for this exam, I'd go back and look at the video of what they did last lecture. Because if you do that and you look at this lecture and you look at the lecture on Wednesday, you are going to have a very good idea of what's going to be asked of you on your final exam. Okay, so that's why I think it's worth the time going over at least the problem types, because if you see this problem, you go, oh yeah, exponential decay, I'm struggling with that. I mean, we can do it here today too, but there is a recording of going over it. Number 19 is another one that was covered yesterday in the lecture series. So this one is a exponential growth problem about mosquitoes. The other one that was covered was number 17, right here, number 17. And this one is a particular, I would say this is a relatively tough problem because it's a little bit more involved. You're finding the interest rate, which is a little bit different than what we would normally do. So number 17 says, what is the interest compounded annually required to double an investment over 12 years? Okay. So number 16, it's an exponential function that's in the form of a quadratic. So that's why, and the way these problems were done was picked on the difficulty of the problem. So that's why on Monday, they're going over these, and these are definitely some of the most difficult ones. Number 15 was another one that was covered last lecture yesterday. Solve the exponential equation, express irrational solutions in exact form. So 15 was, and 14 was the last one covered on the lecture yesterday. All right, so I'm going to cover, I have 6 problems that I like to cover today, and I just also like to welcome Brittany. Brittany, welcome. If you have any questions, Brittany, let me know, because the difference between a live lecture series and a recording is that students can ask questions. So I always feel that's a really important part of these live lectures. So I hope you feel comfortable asking questions. And actually, I'm just going to pause one more time before. All right, we're going to go to number 5 on this review sheet. Number 5 is going to be the first problem that we're going to work through. We're almost there. That's 7. So 5 must be getting close. Here we go, right here. We got number 5. So the first one we're going to do is use the rational zero theorem. All right, so. All right, this can be an extremely long process. Let's see. Perfect. This can be an extremely long process. However, sometimes, and maybe even on your final, you can factor these polynomials by grouping. So we have f of x equals 3x cubed minus x squared plus 3x minus 1. So the first thing we should always try is factor by grouping, because if it factors by grouping, we save ourselves a whole lot of time, a whole lot of headache. So we group the first 2 terms together and we ask, what is 3x cubed minus x squared? What do they have in common? Well, they both have an x squared. So we've got an x squared. And then what are we left with? Well, that's going to be a 3x. And then x squared divided by x squared is 1. So it's going to be 3x minus 1. And 3x minus 1 on the right over here, they have nothing in common, right? So if they have nothing in common, you can always take out a 1. And that 1 is pretty much just a placeholder to help us factor. And then what does the whole thing have in common? They both have a 3x minus 1. So that's going to go out to the front. And then what we're left with is an x squared plus 1. All right. Look, I'm going to pause here just very quickly, see if there's any questions. All right. So this is now our function. We have factored our function. And this one says, and we got to read the directions pretty carefully a lot of times. So it says find the real zeros of f, right? So we want to know when this thing is equal to 0. So when it's equal to 0, we just set each individual factor equal to 0. So we're going to have 2 of them, and I'm going to bring it over here just because I have space. We need 3x minus 1 to equal 0. We're going to add 1. So we get 3x equals 1. And then we're going to divide by 3 to get the x all by itself. So x equals 1/3 is one of our zeros. That's one of our zeros. All right. And then we're going to have x squared, right? The other factor is x squared plus 1 is going to be equal to 0. We subtract 1 on both sides. We get x squared equals -1. And here we'll take the square root on both sides. And when you take the square root on both sides, you have to remember a plus or minus sign. So the square root and the square cancel each other. We get x equals plus or minus the square root of -1. Well, this is not real. This is not real. It's not real. So it is not going to be an answer above. So when it just says find the real zeros of f, there are some real zeros. And what are they? 1 divided by 3. And if we can be as careful as possible with my math lab already put the x equals, right? My math lab already put the x equals. So we're not putting x equals. We're just putting the 1/3. Okay. And then the second part wants to know the factored form. Well, we actually got the factored form first because that's how you should do the problem. The factored form is going to be 3x minus 1 times x squared plus 1. That's the factored form. And again, we actually got that first, which is why sometimes I think my math lab is a bit confusing, because if we were to do this problem on paper, we would do it this way. We would get the factored form first, and then we would get the real zeros. So that's all right. Let's pause this one here. Let's pause. This was number 5 on this review packet. Okay, so here we go. We have a solve the following inequality, okay? And we know it's quadratic because it's x squared. So it's x squared minus 2x plus 9 is less than or equal to 0, okay? So what we would try to do first, always, so we want to graph this thing, okay? And to graph a quadratic, so we can graph a quadratic. So if it's an inequality, so this is my advice. If it's a quadratic inequality, no, one good option is to graph it. If you're more comfortable using something like a sign chart, because this class introduces a lot of different ways that you could solve an inequality. Because it's quadratic and we spent quite a bit of time graphing quadratics, I would go ahead and graph if it's a quadratic inequality. And then this is asking, right, if it's less than or equal to 0, we're looking for the graph when it is below the x-axis. Okay. So a great way to graph a quadratic is we have x squared minus 2x plus 9 is less than or equal to, well, whatever. We're just graphing the quadratic, so we're just pretending this is a function, right? And then a is going to be 1, b is going to be -2, and c equals 9, okay? And so to find the vertex of a quadratic, the x value of the vertex, I like to call it xv, is -b over 2a. So our x value of the vertex, excuse me, is going to be negative. Oop, that was a -2. I'm sorry, right? B is -2 because it's -2. So it's going to be -2 divided by 2 times A. So A is 1. A negative times a negative is positive. That's 2 divided by 2, which is 1. The x value of the vertex is 1. The way we find the y value of the vertex is you just plug in the x value. Plug in the x value of the vertex. Well, if we plug in the 1 into here, we get 1 squared minus 2 times 1 plus 9. That's going to give us, let's see, 1 squared is 1 minus 2 plus 9. Well, this is 1 plus 9 is 10. 10 minus 2 is 8. 10 minus 2 is 8. All right, so 10 minus 2 is 8. When we graph this thing, we know the vertex. Oh, we know the vertex. The vertex is 1, 8. Okay. And typically, if we're graphing quickly, you want to find the vertex. So when we're graphing, you want to find the vertex. And there's a whole bunch of different ways that you could graph quickly, but finding the vertex is good. And then if you want to find the y-intercept, the y-intercept happens when x is 0. So the vertex is what we're going to graph. The vertex here is 1, 8. 1, 1, 2, 3, 4, 5, 6, 7. Oh, 8. It's up here. And the y-intercept, what happens when x is 0? So what's f of 0? Well, everywhere you see x, it's 0. So it's going to be 0 squared minus 2 times 0 plus 9. Well, f of 0 is 9. So the point 0.9 is on our graph. The point 0.9 is on our graph. And that vertex is where it starts. So our graph is going to look like this. Okay. There are a bunch of different ways that you could do it. You also could look at x squared. And because A is positive, if A is positive, we know that it opens up. We know that this thing opens up. So if you have the vertex and you know it's opening up, you can see what this thing looks like. And we're asking the question, when is this graph below the x-axis? Well, it's never below the x-axis because its vertex is above and it opens up. This thing is never below the x-axis. Our answer is there are no real solutions. Okay, there are no real solutions because this graph never goes below the x-axis. All right, that was a lot of information shared very quickly. We're going to pause. All right, so in number 4, we're given a graph. And we want to use the graph to solve the inequality. So we need to know what the inequality means. So down here in part A, the solution set for f of x is less than 0. So when f of x is less than 0, we're looking for where the graph is below the x-axis. Okay, and in fact, let's color code this. How good can we do this? We can do this pretty good, probably, maybe. So we're going to color code that in orange. So in orange, we're looking for where the graph is below the x-axis, right? And it can't touch the x-axis. So when we're doing this, because there's no equal to, we just want to be reminded that we're going to use parentheses on our numbers, okay? So what are the points where it's equal to 0? Well, at 0, it's equal to 0. And what happens after 0 is it starts going down and then it starts coming back up again. So from 0 to 1, we are below the x-axis. Because it says less than, we're going to use parentheses. Had that said less than or equal to, we would have used brackets. Okay. So there's another area though, because what happens with our graph is after 1, it's above the x-axis. So after 2, it starts going down again. So it's going to be union from 2, and then it never comes back up. So from 2 all the way to the right, which we say to infinity, from 2 to infinity, it's below the x-axis. Okay. And if it is helpful to you, you can get rid of the entire top part of the graph because you don't worry about it and it doesn't matter. All we care about is where do we see graph below the x-axis. All right, so if it's helpful, scratch it out. Don't even look at it. All right, but we need to do the next problem, so we're not going to scratch it out. So part B, that's part A. We'll do part B in another color. Part B says, when is f of x greater than or equal to 0? Well, this is asking where the graph is above the x-axis. Okay, and we are going to use on this one, we are going to use brackets. We're going to use brackets on the 0 because the equal to possibility. On part A, it's not equal to, but on part B, it can be equal to, so we're going to use brackets. So let's look where it's above. Well, the graph actually starts above. So from negative infinity, which always gets a parenthesis, right? Because it's not actually a number, all the way till 0, x equals 0. From x equals negative infinity to x equals 0, we are above. And then we end up going below. And in fact, if it's helpful, just get rid of the bottom. Don't even look at it. It doesn't matter. When does it start up again? Well, it goes up and then back down, and that's from 1. Oop, I put a parenthesis and then a bracket. That was weird. From 1 to 2. From 1 to 2. In fact, I'm going to get rid of the purple. It's easier to see where it's above or below, but we actually need the points. Right? The points are from 1 to 2. So union, so from here to here, it's 1 to 2. 1 to 2. Okay. Not every question on your final exam requires a lot of computation. Sometimes a problem on your final exam just requires understanding of the topic. What does it mean for a graph or a function to be less than 0? What's that mean for the graph? For the graph, that means you are below the x-axis. And what's it mean for a function to be greater than 0? That means you're above the x-axis. All right, let's pause the recording here, see if there are questions. All right, so our next problem is dealing with composite functions, okay? And we're finding quite a few composite functions here. And I'm going to write some of the stuff out a little bit bigger so we can see it. F of x is going to be equal to the square root of x. And then we have g of x is equal to 5x plus 3, okay? And it's nice to write out what your domain is right away on these functions. It can be helpful. So the domain on f, the square root, you cannot take the square root of a negative number. So the domain here is negative infinity, not negative infinity. It's going to be 0. You can plug in 0. And actually 0 is going to have a bracket on it, right? So bracket, because you can take the square root of 0. You just can't take the square root of a negative number. The domain is going to be from 0 to infinity for f. For g, I mean, the only things we're really looking for when finding domain are square roots or division. G doesn't have any square roots and it doesn't have any division. The domain are all real numbers, negative infinity to infinity. Okay. So when we're finding something like in part A, we want to find f of g of x. Okay. And I really dislike this notation. I like the function notation better, which will be f of g of x. And the reason why I like this notation better is because you can just substitute g of x right away. What this stands for, or what f of g of x means. In f, everywhere you see x, everywhere there's an x, you're going to write g of x instead. Okay. But I usually take it one step further and I do the substitution first. So it's going to be f of, instead of writing g of x, I write what g of x is equal to, 5x plus 3. And then this means everywhere in x, I write, instead of g of x, right, we're just going to write 5x plus 3. All right, so we go up, right, we're looking at f of x because our one on the outside is f. We see a square root sign, we need a square root. We see an x, what are we going to write? 5x plus 3. So this is when they ask f of g of x, what is f of g of x? We would put in the square root of 5x plus 3. That's what we put in for that answer. That's what f of g of x is. Now we got, what's the domain of this thing? What's the domain? Well, there's a square root. Anytime there's a square root, you set everything inside the square root to be greater than or equal to 0. You cannot take the square root of negative numbers. Anytime there's a square root, to find the domain, you set everything inside, and I'm writing that out. So when you're finding domain, if x is in a square root, you're going to take everything inside the square root and set it greater than or equal to 0. So on our problem here, x is inside a square root. Set everything on the inside of the square root, which is 5x plus 3, greater than or equal to 0. And then we solve this thing. Then we solve it. We're going to subtract 3. We are going to get 5x is greater than or equal to negative 3. Divide by 5. Divide by 5. X is greater than or equal to negative 3/5. We can put that on a number line to give us the interval notation. Put in negative 3/5. And we are going to the right. So it's a bracket. And we're going to the right. So for the domain, it's going to be a bracket, negative 3/5, comma, infinity. That's going to be the second part. All right, I'm going to pause here. All right, so a wonderful student pointed out the fact that we need our domain. We're supposed to type it as an inequality. So we do not write it in interval notation. So our answer is over here. Our answer is over here. And they already put the x for us. So it's going to be x is, well, we don't write the x. We just write the greater than or equal to negative 3/5. That is our answer right there. They wanted it as an inequality. They did not want it as interval notation. So thank you so much. All right, we're going to pause there. All right, so we completed part A of this problem. We're going to now do part B. We're going to do part B of the problem. So we've got g of x, and I'm just rewriting it so it's a little bit bigger, 5x plus 3. This domain was x is greater than or equal to 0. This domain was all real numbers, all real numbers. All right, so now we want to do part B. Part B is g of f of x. And I generally hate the way that looks. So I always use g of f of x, okay? I much prefer the function notation on this, much prefer the function notation, because then it just becomes a substitution problem. This means in g, everywhere that there's an x, instead of writing x, you're going to write f of x. Okay, and we can color code it. We know what f of x is. F of x is the square root of x. So this is really going to be g of the square root of x, which means everywhere in x, everywhere in g, everywhere there's an x, we write the square root of x. So we go to G. We go down to G. We see a 5 in G. Well, we write 5 because it's now we see an X. What do we write instead of an X? A square root of X. And then we write a plus 3. And that is that is G of f of X. So for our answer, we would write 5 times the square root of X. And then we got to be careful. Well, we don't have to be careful. On the computer, you can see it clearly. So it's plus 3. You also could have written as 3 plus 5 square roots of X. All right, now the domain. How do we find the domain? Well, if X is in a square root, you set everything under the square root to be greater than or equal to 0. So this domain's super nice. It's just X is greater than or equal, except you don't write the X, right? We got to be very, very careful with MyMathLab. You just write greater than or equal to 0 because no, I lied. I am lying to you guys. I am lying to you guys because you see this little bar. Ooh, that means X such that. So we have to put the X. You have to put X is greater than or equal to 0. You have to put the X. It does make you put the X because there's a such that right before the box. It's, yeah, I'm sorry. So on the previous problem, you had to include the X. You had to include the X. There is a such that bar right there. So you have to put the X. You have to put the X. If you notice you make mistakes like that on MyMathLab, please email your instructor. Say, on number 17 on my exam, I didn't put the X because it looked like MyMathLab already had the X. Can you please review it? That is something that your instructor should be giving you credit for, in my opinion. My opinion doesn't matter. I'm just a lecturer. And if I was teaching the class, you would get credit for it. But again, the way you enter answers in MyMathLab should not be a skill that you are assessed over in this class, if that makes sense. So please email your instructor. Don't feel like you're bothering them. That's their job. That's what they're doing. All right. We're going to pause here on the recording. Yeah. This one says the function f of x equals x cubed minus 1 is a one-to-one function. Find the inverse of f and check your answer. So the way that we find an inverse, and if we want steps to the inverse, let's go ahead and write that up. Steps to finding the inverse. All right, first step, change f of x to y. Okay, so we have f of x equals x cubed minus 1. And we're going to change the f of x to y. So it's going to be y equals x cubed minus 1. Step 2. Well, everywhere you see y, write x. Everywhere that there's a y, write x. And everywhere there's an x, write y. Right? Essentially, you're swapping them, especially if there's only 2, you just swap them. So we have x equals y cubed minus 1. And then step 3 is solve for y. And what does solve mean? You get the y by itself. By itself. There we go. So our focus is on the y. We want that y by itself. We got to get rid of the minus 1. So we're going to add 1 to both sides. We get x plus 1 equals y cubed. And then the way we get rid of an exponent of 3 is we take a root power of 3 on both sides. And actually, if we take an odd root power, we don't need a plus or minus sign. So now we get y equals the cubed root of x plus 1. And this is our answer. That is our answer. Step 4 is the last one. Change the y to f to the minus 1 of x equals the square root of x plus 1. Oh, well, yeah, for us. So for us, it's going to be f to the negative 1 of x equals the cube root of x plus 1. So this is part A. This is the answer to part A. It asks you to check your answer. I just wouldn't check your answer. As long as you didn't make any mistakes, that will always be correct. So there are some areas that we had to check our answer, like when we're solving radical equations. This is not one of those times. This will work. This will work. So now we need to find the domain and range of the function and the inverse. Okay. This is great practice. This is great practice. So now that we found the inverse, I'm going to go ahead and get rid of those steps to finding the inverse, if that's okay. Let me pause it here for a minute in case you're taking notes. So we want to know the domain. We want to know the domain and, I know what I was going to do. We're going to get rid of those steps here just to free up some space on the screen. All right, so what we're going to do is find the domain and range of the function. Now, we just look at the function and we just look at the inverse. The only thing you're ever finding is the domain. So what's the domain of this thing? What is the domain of f of x? The domain of f of x is, well, do we have any square roots? There are no square roots. Do we have any division? There is no division. If there are no square roots and there's no division, there are no problems. There's no problems whatsoever. So ours is going to be from negative infinity to infinity because there are no problems. Okay. Now, what's the domain? So now we're finding the domain of f to the negative 1 of x. That's the cube root of x plus 1. Well, are there any square roots? Well, there is a cubed root, but there are no square roots. So there's a cube root, but there's no square roots. So there's no square roots. Is there any division? No, there's no division. There's no problems here either. There are no problems, which means the domain of the inverse is negative infinity to infinity. Now, what do we know about the range? The range, I'm going to color code this, hopefully. The range of the original function is the domain of the inverse. And I will write that out. I will write that out. This is the most important part for your final, knowing that the range of f of x is the domain of f to the negative 1 of x. This is vital information that you need for your final, okay? You have to know that fact. If they tell you the domain of the inverse and they ask you for the range, it's the same thing. It's the same thing, okay? And then the next statement that you need, the next statement is the range of f to the negative 1 of x is the domain. Okay, so when they ask us for the range of the inverse function, the range of the inverse function is the domain of the regular function. Okay. So even though on this problem, everything is negative infinity to infinity, so it's pretty boring, on your final, you need to know these two facts. You need to know these two facts. Even though, again, I know the problem that we have here is pretty boring. The problem on your final will be, the domain and range will be different. They'll be different. On the, well, yeah, if that, all you ever find though is domain. So you find the domain of the regular function and you find the domain of the inverse, and you get the ranges with these facts that are boxed. All right, so that's how we got domain and range. Now to graph these things, well, we're going to graph using transformations. So we know that f of x was, what was it? So we don't mess up. It was x cubed minus 1. We should know what the graph of x cubed looks like. The graph of x cubed looks like this. And then the minus 1 makes it go down 1. So ours is going to look like f of x or x cubed, but it's going to be down 1. So ours is going to look something like that. Okay. Mine's not perfect. You don't have to be perfect because you're going to be matching, right? So we can get rid of this. All right. And now, what is the inverse function? The inverse function was f of -1 of x equals, it was x plus 1, the cube root of x plus 1. Well, the cube root, just the cube root by itself, the cube root by itself looks like this. That's the cube root by itself. Well, our cube root isn't by itself. There's a plus 1 on the inside, which means it belongs with the x. If it belongs to the x, it's going left or right. X's always do the opposite. So this is going to go to the left. There we go. Left 1. It's going to go to the left 1. So all these points are moved to the left 1. All right. And again, my picture, probably not even that good. It's probably bad, but it's good enough to select the correct multiple choice. And then they said they wanted the line x equals y or y equals x, because if you're good, if you're spatially good, which I am probably not, and my art is also not good, if you flip the blue over the line y equals x, you end up with the red. And you can see it in some specific ordered pairs, right here, some specific ordered pairs. That's what's supposed to happen. When you flip it over the line, if you reflect it over the line y equals x, it's supposed to land on top of each other. So when we go to the graphs, we can go to the graphs right here. Can we make these bigger? I mean, we can. Automatic zoom? No, give me lots of zoom. There we go. When we go to the graphs, this D, if we're looking, D is our answer. I didn't do a very good job, but I know that D is the answer, because you don't have to do a great job. You just have to do like an okay job. D is our answer, because that's the one that looks like our drawing. D looks like our drawing. See, that's our drawing. They intersected up here. Oh, they intersected up here. That's our drawing. I mean, what's kind of nice about multiple choice questions is it really can't be B, because they don't fold over each other. It can't be A. Do they fold over each other? Probably not. Maybe they do. Yeah, they probably do. Anyway, that's okay. We'll pause it here. See if there's any questions on this. Fine, this is your time. All right, use the given function f to answer parts A through F below. F of x is the natural log of 2x plus 3. Okay, so the domain. Logarithms, similar to square roots, except in a logarithm, so if you have a logarithm, the domain, if x is in a logarithm, right? And the natural logarithm is a logarithm. What you're going to do is set everything inside the log to be greater than 0. A logarithm cannot be equal to 0, so it has to be greater than 0. So for us, the domain is going to be 2x is greater than 0. We're going to divide both sides by 2. X is greater than 0. And now this one says your answer has to be an interval notation. So we put that on a little mini number line. 0, we are greater than 0. So this is going to be 0 to infinity. That's going to be our answer for part A. For part B, it's really, really helpful to know what the natural log of x looks like. So the natural log of x, if we just have the natural log of x, it always goes through the point 1, 0. So it always goes through the point 1, 0, and then it's not L-shaped. That's what it looks like. It's good to know the shape. It's good to know the shape. There's no letter in the alphabet that looks like that. All right. So on ours is the natural log of 2x plus 3. This 2 is multiplication. It belongs to the x. It's actually going to divide your x values. It divides your x's by 2. X's always do the opposite. Instead of multiplying by 2, it halves it. So what happens is this point 1, 0 becomes 1/2 0. So now we're at 1/2 0. And in fact, all x values get halved. All x values get halved. It's getting compressed horizontally. Compressed horizontally. We don't have to be perfect. All right. So then what do we have to do next? We have to, the plus 3. The plus 3 makes it go up 3. So we're going to add 3 to our y's. Our new point is the point 1/2, 3. Our new point is 1/2, 3. We know that 1, 2, 3, 1/2, 3 has to be on our graph. Okay. And then it's the same shape. It's compressed sum. It's compressed sum. Okay. There's only one graph that looks like that, right? It's got to be B. I mean, right? It's got to be B, right? Yeah, it's got to be B. B is our only possible answer for this one. Okay. We're going to pop back and copy over. So transformations is still a big part, even though we did it before. Still a big part of the course. Any questions on those transformations? I'm going to put this down here. I don't want to mess up any of the work that we just did. So we'll put the rest of it. All right. And so, it's probably also good to know because it talks about the asymptotes too. It says the graph determine the range and any asymptote. So on a logarithm, the asymptote always starts at x equals 0, right? And then we have to divide by 2. But if we take 0 divided by 2, we still get 0, right? So after the green, it's still 0. It's x equals 0 over 2, which is x equals 0. So our asymptote here is, there is a vertical asymptote. It already says x equals, and ours is 0. All right, what about our range? This one says the range is, well, the range goes from -infinity to infinity. How low does this graph go? It goes as low as you want. How high does it go? Goes as high as you want. That's fine. That's a little confusing. I'm not exactly sure what I asked about range, because range of a logarithm is always going to be -infinity to infinity. All right, now let's find the inverse. So how do we find the inverse? We change the f of x to y. Y equals natural log of 2x. Oh, something weird happened. 2x plus 3. Then everywhere you see y, write x. Everywhere you see x, write y. So it's going to be natural log of 2y plus 3. And now our job is to solve for the y. Get this y by itself. What are we going to do? Subtract 3 on both sides. We're going to get x minus 3 equals natural log of 2y. And now how do we get rid of the natural log? Well, you can either rewrite it or you can take e. E is the base. E is the base of an exponential on both sides, because then e and natural log cancel. You're left with e to the x minus 3 equals 2y, and then divide both sides by 2. For our inverse, we end up with the inverse is equal to 1/2 e to the x minus 3. All right. And now find the domain and range of the inverse. Well, the domain of the inverse, an exponential function, its domain is always -infinity to infinity, always. What's the range? Well, okay. And also, we know the original function, the range of the original function is the domain of the inverse. These two answers are always the same. And what's the range of the inverse? The range of the inverse is the domain. So what was the domain of the regular one? We have it up here. So these two answers are always the same. Let's color code it. The domain of the regular function is always the same as the range of the inverse. So that's 0 to infinity. And now when we're graphing, if we graph just the graph of e to the x as an asymptote at y equals 0, and it goes through the point 0, 1. So we're through the point 0, 1. That's what e to the x looks like. But what are we doing to it? Well, this minus 3 in the exponent means it's going to the right 3. So we're going to the right 3. It's going to now be the 0.31. This 1/2 is on the outside. It belongs at the y. It does what we want. It multiplies our y's by 1/2. So we're going to have the 0.3 and then 1/2. So we need the 0.3 1/2. That's this. That's A. A is going to have it. A is going to have it. So A is going to be the correct graph there. All right. I'm going to pause the recording.